Swayam Prabha. Digital India. Educated India.
Thank you. I thank the organizers for giving me this opportunity to give two talks on what can be called a traditional Indian mathematics. So today I will be talking about some developments in geometry, algebra, combinatorics, and a little bit of trigonometry in India. Okay, next please. See, first of all, in fact, I have to say that nowadays when they talk about Indian mathematics or Indian science and all that, immediately they will say Vedic mathematics, Vedic science and all that, Somehow this is not correct because everything is not, in Vedas. I mean, everything didn't follow from Vedas. Of course, many things did, many things originated. So it is not correct to say, that it is Vedic mathematics. So I will say that traditional Indian mathematics, which is practiced in India from the Vedic times up to modern times. Okay, and of course, the modern times now, a lot of prominent mathematicians from India, but they may not be doing traditional mathematics, they are doing modern mathematics. Anyway, so now all important developments in mathematics till say 17th century had Indian connection: arithmetic, geometry, algebra, trigonometry, combinatorics, calculus. Okay, so now you have to be careful. I am not saying that everything was there. I am saying that important developments had some Indian connection. Okay, I mean Indians had something to say about it. Not that they had everything to say and everything was done there. I am not saying that. Okay, that is an Indian connection. Okay. So in a recent lecture, the famous mathematician Manjul Bhargava, how many have heard about it? Him? Manjul Bhargava is a famous mathematician of Indian origin, and he keeps visiting India also often. He got this Fields Medal about I think 15 years back or so. Fields Medal is equivalent to Nobel Prize, So because mathematics, Nobel Prize we don't have for mathematics. So Fields Medal is equal. Is awarded only once in 4 years. So that's an important thing. And he, of course, had some reasonable understanding of Indian mathematics. So that is because he used to, early I think childhood, he spent a few years here, and then also his grandfather was a great Sanskrit scholar and who knew something about this Indian texts in mathematics and all that. And he gave a recent lecture about a year back or so. So he lists the following major Indian contributions. Okay, so I am not following him fully. I am just as a reference kind of a thing, I will add quite a bit to what he is saying, but just as a reference template, what he is saying. Okay, zero and Indian numeral system. That is the decimal place value system. So it is we all know what is the importance of this decimal place value system. Okay, even in Vedic times it was there in a way, not place value system. They had words for powers of 10, dasha, shata, sahasra, laksha, koti, and all that. That is sometimes it's called decimal numeration. Okay, and that is not the place value system. Later it developed. That means whatever number you gave, if you write a number, then the digits are 1 to 9. Okay, and that is of Indian origin, that you have digits from 1 to 9 and 0. Okay, so the value of that number depends upon its place. So place value. Okay, and 0 is of course an important thing. It's not only it holds a place. So some power 10 it is not there. So then you put 0, but also is a value. Okay, so placeholder and value. So I will not go into too much detail about it because that is one thing which is somewhat well known. Okay, and there is a very good book called Universal History of Numbers by George Ifra or so. So that is a good book that gives the whole evolution of this number system and how it came about. Now the Indian decimal place value system, see Laplace is one of the great mathematician, physicist, astronomers, so French person between I think 18th and 19th century. So Laplace has this to say, it is India that gave us the ingenious method of expressing all numbers by means of 10 symbols, each symbol receiving a value of position as well as an absolute value. A profound and important area which appears so simple to us now that we ignore its true merit, but its very simplicity and the great ease which it has lent to all computations put our arithmetic in the first rank of useful inventions. And we shall appreciate the grandeur of this achievement the more when we remember that it escaped the genius of Archimedes and Apollonius, two of the greatest men produced by antiquity. So that is they are Greek, of course. Yeah. Next. Yeah. So now next thing Manjul Bhargava listed is Bauddha Pythagoras theorem. We know this Pythagoras theorem, all of you would be knowing about it. A clear enunciation of the so-called Pythagoras theorem is described in what is known as the Bauddha Sulba Sutra around 800 BC. It states it unequivocally. You see, one has to be careful. I mean, I am not saying that it was not realized. Okay, probably Egyptians knew it, and because it is not possible to construct these pyramids and all that without some knowledge of this Pythagoras theorem. And similarly, Babylonians, I mean 1300 BC or 1000 BC, they would have known it because they talk about various things. In the tablets there is indication that they may know about it. See, 3, 4, 5 is called a Pythagorean triplet. Okay, 5, 12, 13, right? 3 squared plus 4 squared is equal to 5 squared, and 12 squared plus 5 squared is equal to 13 squared, and all that. So they knew about it, but the very clear statement, that is there only in Bauddha Sulba Sutra. So Dirgha Chaturashtrasya Akshaya Rajjuhu Parshvamani Triyangmani Chayat Prutak Bhute Kurutaha Tad Ubayam Karoti. So they are always talking about the ropes. Okay, I mean that is because they are talking about the construction. Sulba Sutras are about mathematical manuals for constructing Vedic altars, okay, of definite shapes and all that. They all should have tiles, okay, and they should have some definite shapes and sizes, with appropriate proportions, So if one can't have arbitrary sizes, one should have a specified kind of a thing. So for all that, geometry is needed, and so they all use this rajju, or this rope, and it is called shulba in Sanskrit. So that is used. So that's why they are talking about rajju. So rope corresponding to the diagonal of a rectangle makes whatever is made by the lateral and the vertical sides individually. So here Dirgha Chaturashram means rectangle, and Akneya Rajjuhu means diagonal rope. Parshvamani Triyangmani means the lateral side and perpendicular side. So I clearly say that square on the diagonal of a rectangle is equal to the sum of the squares on the two sides. Okay, next please. See, now they using this, they give various kinds of constructions. Okay, in this Bauddha Sulba Sutra, there are many other Sulba Sutras also. Mahanava Sulba Sutra and so on. Katyayana Sulba Sutra, like that. So for instance, one of the important things is, so suppose you have a square, okay, of some side, two squares of sides, let's say A and B. Then you have to construct a square whose area is equal to sum of the areas. Not sum of the sides, it is very easy. Sum of the areas must be equal to the constructed square. Its area should be sum of the squares of the given squares. Okay, so that is what is done is, see, suppose these are the two, A, B, C, D, that is one square, and I, C, G, C, G, H, I, that is another square. Okay, so then essentially Sutra says that you mark a BE here. You see, E is located such that BE is equal to the side of the small square. Okay, so then join this diagonal AE. So then the square on that is equal to the is equal to sum of, so sum of the square. So this is the required square, okay, AEHK, okay. This is sort of, I mean, they don't give proof as such, but this is somewhat, a proof is somewhat implicit in it, I will say, because you see, in this is the original squares, right, this one and this one, okay. So now this square, okay, sorry, this rectangle you displace it and put here, and this right angle triangle you put it here, okay. So then essentially, so the sum of the this area is essentially equal to the sum of the two areas. So that is what is happening, okay, yeah. So I mean, there are many other things also, you know, Sulabha Sutras give, for instance, converting a rectangle to a square, and then a very interesting thing is about, you know, given a square, to find out a square whose area is n times the given area of the given square, okay. So that is not so simple, right, because you have to have root n, you see. So the area must be n into a square. So the side must be root n into this. So without calculating and all that you have to do, okay. So they have given a nice construction, you know, which is equivalent to, you know, its uses basically, you know, a plus b whole squared is equal to a squared plus b squared plus 2ab kind of a thing, you know. I will not go into that in detail, okay. That is, remember, this is in 500 BC, 600 BC, like that, okay. So now the next thing that Bhargava said was mathematics of language. So this is a Pauninian generative grammar. So it has been now recognized, you know, the importance of this grammar of Sanskrit called Paunini's this thing was a person, and he wrote a work called Ashtadhyayi, okay. So he told how to generate all possible words, okay, given some roots kind of a thing, you know, which are there in common parlance. So that gives the rules for that, you see. So in a way, this language, this grammar is in a mathematical kind of structures, and so it gives the rules for that. So sutra or algorithmic format. In fact, many people say that the Indian mathematics and astronomy and all that are patterned after Paunini came before, you see, patterned after the Pauninian grammar, you see, just like all the Western, I mean, essentially Greek and then what followed, you see, it was all the reference thing was the Euclidean thing, you know, Euclidean geometry was the model, and then from that, you know, you write all kinds of results and all that you do and things like that. So here the model was the Pauninian thing, and you have got sutras for everything. So that is the mathematics of language. In fact, the very word algorithm is derived from the name of the famous 9th century Islamic mathematician Al-Khwarizmi, who was greatly influenced by Indian procedures in mathematics and wrote the famous book Kitab al-Hisab al-Hindi on the art of Hindu reckoning, okay. So it is well known that at least in the from let us say some 6th to some 9th or 10th centuries, Arabs were greatly influenced by the Indian mathematics, astronomy and others. I should not say just Arabs, you can say Arab Islamic, okay. So there were non-Muslim Arabs also and non-Arab Muslims also, you see. So in fact, this Al-Khwarizmi was some kind of a, you know, possibly closer to Tajikistan or so, northeastern part of Iran, okay. So so he wrote that he was a, so this, and algorithm comes from that, and it has some Indian connection, you know, because Al-Khwarizmi was highly influenced by the Indian methods of reckoning, okay. So then the fourth thing is the sine function in trigonometry, which we will take up shortly. I will elaborate on that. And negative numbers. So operations with negative numbers discussed in Brahmagupta's Brahmasputa Siddhanta. So that is a very great work, 628 CE, okay. See, Aryabhatta can be considered as the father of Indian mathematical astronomy in India. That is, he wrote his work in 499 CE, okay, CE. Of course, he wouldn't have discovered everything that is there in the book. He would have, summarized various results that are there in earlier books and also added some things in his own and systematized it. And Aryabhata was the Aryabhatiya is extremely cryptic, one will not be able to understand. One will be able to remember the formula, well, there are only 121 slokas are there, but you will not be able to understand. So naturally commentaries were there, and there is one Bhaskaracharya I, who lived in 7th century. Okay, he wrote a great work called Aryabhata, Aryabhatiya Bhashya, the commentary on that. And his contemporary was Brahmagupta. Brahmagupta is one of the most famous Indian mathematicians. Even now, a lot of people, if they know about Indian mathematics, they would know about Bhaskaracharya and not the second Bhaskaracharya they will know, and Brahmagupta they would know. Okay. Now, the Brahmasputa Siddhanta is a very elaborate book. It is mostly an astronomy, but there are some 2 chapters on mathematics, very, very significant chapters on mathematics in that. Because see, those days, you see, astronomy and mathematics went hand in hand. Not only in India, in other places also. You see, all astronomy was lot of developments in mathematics, was associated with astronomical problems. Okay, trigonometry that is related to astronomy. Okay, and later we will see that calculus is very much was needed in astronomical calculation. So that's why. So it is not surprising that so they had a separate section for mathematics. And it was considered as some kind of much of mathematics was considered as part of this thing, astronomy. Well, later we will see that algebra, he has got a lot of algebra. And so he gives these rules, it's very interesting, the negative numbers are discussed in Brahmagupta's Brahmasputa Siddhanta, and he gives these rules: minus into plus is minus, plus into minus is minus, minus into minus is equal to plus, and so on. So the Brahmagupta's, all these, and also he talks a little bit about zero, but not all operations are what he conceived was correct. But still, it's very this thing. In fact, I don't know whether you might have heard of, there's one Jonathan Crabtree. There's a lot of videos coming, Australian. He is always talking about, that Brahmagupta's negative numbers should be there in schools and things like that, etc. Anyway, that is an aside. So then, he had, Brahmagupta had, 1 minute, yeah. So this, so sixth thing that he says was the solutions to quadratic equation. Okay. So solutions of a quadratic equation discussed in Aryabhatiya. Okay. See, suppose you have an arithmetic sequence a plus d, a plus 2d, etc., a plus n minus 1 into d. So that is the first quantity is a, the common difference is d, and the n terms. Okay. And you know how to sum it. Okay. So that is this. You know that it will be taught in schools. So this is this thing. So given a, d, and n, you can find out s. Now given a, d, and s to find n, see, that is not so simple. Okay, because see, this here n into n is coming. So quadratic equation, and this solution of the quadratic equation is given in Aryabhatiya. This is the thing. Okay. Now, in fact, Aryabhatiya has what is known as a mathematics section called Ganita Pada, which gives algorithms for finding sum of first 10 natural numbers, sum of their squares, sum of their cubes, square roots, cube roots, geometrical results, then the trigonometry, sines. Okay, I'll come to that. Even interest and a capital, and so on. Significantly, it gives the value of pi at 3.1416, which is correct to 4 decimal places. Okay. Of course, he doesn't say pi. What he says is, he gives a circle, whose diameter is 20,000. So then, what is its circumference? Okay. So it will be, and the value implicit is this. And in fact, very interestingly, he will say that it is, this value is asannaha, approximate kind of a thing. So this, I mean, he might have had some intuition about the fact that it is not a rational number. But anyway, he just says asannaha and leaves it at that. Also Aryabhatiya, and also see Aryabhatiya was the first text, which gives great details about, it is very clear that he was very fully, it makes use of the decimal place value system like anything, you see. So that's why many people, all these videos and all that, you are seeing that Aryabhata invented zero, things like that, you see. So that's not quite true, but he was really first person to really make use of this decimal place value system fully, you see, especially in finding square root, cube root and all that, it very clearly he writes the numbers in a decimal manner, decimal place value manner. He also talks about what is known as the Kuttaka algorithm for finding integral solutions of linear indeterminate equation. So, equation in the form ax plus by is equal to cy, where a, b, c are integers. So, you have to solve for integral values of x and y. So, this is him, he gives a method as only in one verse he gives, okay. So, it is difficult to understand, but method is there, okay. Using that you can do it, the algorithm is there. So, that is called the Kuttaka equation. So, you have to solve for integral xy. Naturally, if you do not impose xy, okay, if you any x you can choose and you can find the corresponding y, but what we want is integral values of xy. So, this is the Kuttaka problem. They are also called Diophantine equations, okay, but Indians had much cleverer uses of these things then. Now, Brahmagupta goes further, he talks about quadratic indeterminate equations or Varga Prakriti. So, they are of this form, x squared minus dy squared is equal to k. You have to solve for this. So, d and k are given integers, you have to solve for integer values for xy. And Brahmagupta specifically solves it for, he gives the solution in that Ganita chapter, Kuttaka chapter, 92, d is equal to 92 and 83 and k is equal to 1. So, these are the solution, okay. So, x is equal to 1151 and y is equal to 120. So, similarly, x is equal to 82 and y is equal to 9 solves this equation. Now, apart from this solution, this particular example and solution, what is important is he formulates the composition law called Bhavana. So, if x1 squared minus dy y1 squared is equal to k1, suppose you have this equation, okay. So, d is there and k1 and for k2, okay. So, these are the solution x1 y1 for this equation and x2 y2 for this equation. Then the solution for k1 k2 this is called a kshepa, the right hand side is this. So, once you know the solution x1 y1 x2 y2, then you can find the solution for this. So, this is amazing for 7th century, okay. So, this kind of advanced thing, see people, is aggressively asserted that algebra is Arabic in origin. It is complete nonsense. There is no comparable advanced result like this in in Islamic tradition or Greek tradition and all that. It is quite a sophisticated thing, man. It is not an easy thing. To formulate this kind of a thing in 7th century. So, and later Bhaskara and one Jayadeva also. So, they solve equations of this form x squared minus dy squared is equal to 1, okay, using what is the Chakrawala method. So, they solve it for this d is equal to, that is essentially 61, k is equal to 1, x squared minus 61 y squared is equal to 1. So, x squared minus dy squared is equal to 1, nowadays it is called Pell's equation. And one can show that, and this was considered by Fermat, the famous European mathematician. Brahmagupta talks about it in 7th century, he talks about it only 16th, 17th centuries. And precisely this Fermat throws a challenge to the European mathematicians at that time to solve it for this equation x squared minus 61 y squared is equal to 1. And there are solutions, they are called one of the Lagrange's method and all that. And but this Chakrawala method is somewhat 40% more efficient in general for large G. And Bhaskara gives the solution for this. The solution is this, x is this and y is this. Large numbers. I mean, you can't get it by trial and error and things like that, such large number. You see, you should have a very definite method. Okay. So, he gives the Chakravala method, but of course, fully, I mean, he doesn't show that there is a method, he doesn't show that it is convergent. The process is convergent and you can attain the answer in finite number of steps. But later, people who pursued it, there was one Krishnaswamy Iyengar in last century, he showed that it converges actually, and it corresponds to what is known as irregular continued fractions and so on. We will not go into that. So, this is the advanced kind of algebra, that was there. And when they did in astronomy text, if you see that, you will see that they are not mixing, oh, this is the geometrical method, this is the algebra, this thing. They are mixing all the things, whatever is convenient for the solution of a thing. So, they will use the geometrical method, algebraic method and all. Yeah. So, now you can come to this combinatorics, So, you know this combinatorial problem, permutations and combinations and all that. Okay. So, if you have n objects, okay, so then how many ways are there for arranging it? Okay. Okay. So, r objects out of n, so that is NCR. Yeah, you are right. So, a chapter in Bruhat Samhita Varahamihira, it is, of course, Varahamihira has written astronomy book also called Panchasiddhantika. So, this is more related to astrology, some astronomy is there, and it gives various things, not only that, I mean, predictions, but other things also. It was a chapter called Gandha Yukti, and he says that there are 1822 combinations which can be found by choosing 4 perfumes from a set of 16 basic perfumes. So, 16 C4 is equal to 1820. So, that is, yes, seems to be aware of that. So, now, this, you might have heard of this Pascal's triangle. So, for these binomial coefficients, so that is also given in explained in work by Halayudha on Pingala Sutra. So, I will come to this Pingala Sutra. So, in the construction of this Meru Prastara. Okay. So, he says that suppose there are short syllables and long syllables, like or short beat and long beat. Okay. Okay. So, then suppose there is a metrical form, the total n these things are there, symbols. So, then how many do you have number of metrical forms with or lagus in a verse of n syllables? So, if the total n syllables and suppose or is lagu number or, okay, this or lagus. So, how many form there are there, you see. So, he gives this in this way of construction, he gives it where he is constructing this NCR is based on this. Okay. See, for instance, this is leave this. So, this is a plus b whole to the power of n, it is a plus b. You know that a plus b whole squared is a squared plus 2ab plus b squared and so on, right. So, this is essentially related to that, and see that you see here 2, it is the sum of these adjacent quantities in the row above. Similarly, 3 is 1 plus 2, here 3 is 1 plus 2. Here 4 is 1 plus 3 and 6 is 3 plus 3 and 4 is, so like that he is, and essentially this thing, which is the use of this combinatorial formula. So, in Leelavati of Bhaskaracharya, so the Leelavati is a great work, many of you would have heard about it in 12th century. So, it has arithmetic and lot of arithmetic, little bit of algebra, quite a bit of geometry is there in Leelavati. So, and he gives extremely good examples, lot of illustrative examples are there which are related to what people knew and related to the society. So, he says that how many variations in the form of God Shambhu with the exchange of his 10 attributes held reciprocally in several hands, rope, elephant, sook, serpent, tabor, etc. You see 10 of them, arrow, bow and all that, you see. And those of Hari, you see, suppose mace, discus, lotus and car. Shankha, Chakra, Gada, Padma. Okay, 4 of them. You see 4 hands he is holding. How many ways are there? Okay, so he gives the answer. Okay, and that is this factorial 4 for the 4, and Shambhu it is factorial 10. Okay, so these are all somewhat related to what. See, for instance, in a place called Badami in Karnataka, you see there is caves, beautiful cave temples are there. Cave, this thing. So there is a figure of Shiva with 10 hands. I think it's about 7th century or so. So possibly Bhaskara was inspired by that. Okay. Now also we know that suppose the number of combinations, see it is if many of these objects are identical, then the number of ways one has to be careful. Okay, one has to be careful about the number of ways, right? So so this he says that Bhaskara says let there be n digits, p of them are d1, q of them are d2, r of them are d3 and all that. So then the number of permutations is factorial n by factorial p, factorial q, factorial r, etc. that comes in the denominator. Okay, because factorial n of course is the total number of permutations, but suppose that d1 if you take, there are p of them, and if you rearrange them, you see does not give to new arrangement. So you have to divide this by that. So similarly for other things. So this is the. So now we will come to what is known as Virahanka. What is known as Fibonacci sequence. So which is discussed in one Virahanka, a work called Vrutta Jati Samuchaya around 600 BC. So this is he is talking about this. See the rules for meter, poetical meter, that is there in Pingala Chandas Sutra, that is 300 BC or so. He has given many results, but it's extremely brief. So he also has indicated this sequence, but not very clearly. Okay. So now Virahanka explicitly says that, see suppose there is a metrical forms with matra, you can say some value, the short syllable and long syllable. Okay. So suppose you associate value 1 for Lagu and 2 for Guru. Okay. So and if any matra with n these things, you have to add up all the values. So if whenever there is a L occurs, you have to put 1. So whenever there is a G occurs, you have to put 2. So you have to sum up all these things. So this is this number of metrical forms. This thing. Now suppose the matra n is there. What is the number of possibilities Sn with lagus and gurus with matra n? Okay. So this. Suppose there is value 1 matra. You see, it can only be lagu. That is all, because value 1. And if it is 2, so it can be guru, because guru has the value 2, and 2 lagus also have this. So it is 2 matras. So that is the 2 ways of doing it. And if you have 3 matras, it is you will have 3. You can see that this is the thing. 3 matras are there. So 1 L and 1 G, 1 G, 1 L, then 3 L. So and it is clearly see that this is equal to the sum of the previous ones. So now you see, you can see that this is you can generate from this, because the last thing can be either guru or lagu. So if it is guru, then attach one G here, so you will get this, and the last one if it is L, so you have to put L in both here, okay, here and here. So it's essentially this plus this number plus this number. Similarly 4 matra, it is these things, and you can see that So either this one you attach a G, so you get this, and here these things you attach an L. So S4 is S2 plus S3 5. So continuing in this way, it's clear that Sn, that is metrical forms with value n, okay, matra n. So that is Sn is equal to Sn minus 2 plus Sn minus 1. This is what is known as popularly known as Fibonacci sequence, and this is called Fibonacci numbers. But actually this is done much earlier. In Virahanka he has given it in 600 BC itself, and this is this sequence. And this has applications in various things, okay, flower pattern and all that, right? You people know about it, and also of course number of beats and all that, possible beats, if in a percussion instrument, this Bhargava keeps on talking about, because he is into this tabla also, you see. So long this thing, tala and short tala, okay. So what is the, suppose you assign value 1 to short tala and this thing 2 to this thing. So given the number and how many, see, that is the, you might have seen the videos, yeah. Oh. And then next he talks about this error detecting codes or correcting codes, because Vedic recitations, words, so there is lot of Vedas were earlier transmitted through oral transmission, okay. So then you have to find the exact sequence in which various things are uttered. One has to be careful. So there, sometimes you vary these things and then do it in a different order and all that, so that finally you will be able to, so all the errors will be avoided, okay, because various ways are there, and then, so that is the error detecting thing he has got. And then first exact formula for pi, so means the infinite series for it. So this is the so-called Madhava series, okay. Of course, it is not written like this. It said the circumference of a circle is 4 times the diameter, then divide by 1, then divide by 3, divide by 5 and all that, and successively add and subtract. So that is the circumference. So in the way it is, shloka is written, Vyase Varidhi Nihite Rupa Krute Vyasa Sagarabdi Hate Tisharadi Vishama Sankhya Bhaktam Runam Swam Prutak Kramat Kuryati. This will give the, so these how things are expressed. These how things are expressed, that is shloka. So it is quite unambiguous, So when people say, Sanskrit shloka, there is a lot of, ambiguity in meanings and all that. That is not true. Not for everything, you see. There may be in some Sahitya, there may be some ambiguity. But mostly mathematics astronomy means that precise meanings are there, for the various terms. And mostly one can see the unambiguous meaning. Of course, sometimes there may be some small controversies, but mostly one can always, this is the meaning assigned to that. D is the diameter, yes. D is the diameter, yes. D is the diameter, C is the circumference. So Vyasa is the diameter. Varidhi, you see, in the word numeral notation, Varidhi stands for 4, and Nihate means multiply, Rupa Krute, divide by 1. So why do you divide by 1, it gives the same thing, but then it will be clear next things. Then again, Vyasa Sagarabhi Hate, Vyasa is again diameter, and then Sagara stands for 4, multiply by that. 3, Shara stands for 5, okay. Sharadi, again Shara and etc. Vishama Sankhya means odd numbers. So you divide by this 3, 5, etc. odd numbers, and then divide. Bhaktam is the thing. Runam, negative. Swam, positive. Prutak, separately. Kramat in order. Kuryat, let it be done. See, this is what it means. Yeah. Okay. Similarly, infinite series for sine and cosine. Okay. So I will take this needs some elaboration. I will take it up in the next lecture. Radian measure, see, they will always talk about, in a way they did, but they don't say, see, I will tell you. What they mean is, whenever they talk of a arc and, chord and all that, they all talk of lengths only. Yeah. Yeah. See, I will tell you. So what they say is that, sine function, yeah. I will come to that, yeah. So they will say, for instance, that the circumference of a circle with circumference 21,600, the radius is nearly 3438, they say. So 21,600 and 3438. Essentially, 3438 is the number of minutes in a radian. So they only talk about the arc and this measure and length and all that. But all results will follow. There is not necessary to multiply, to the radian. It is implicitly there. Yeah. Anyway, we will come to that. We will, I think, see. And yes, I'll come to that. Yes, I'll come to that. Yeah, the general formula for tan inverse also is that. Yeah. So that is actually simple extension of that. When I draw the figure, it will be. Yeah. So the proofs in Indian mathematics, sometimes they say that they are mostly had various results, but did not have proofs. But there are proofs, but not the Euclidean way. You start with some axioms and then do these things. So it is one of the rationale or demonstration or yukti, satisfactory method to understand a result. Okay. So that is the thing. See, for instance, that Bodhayana theorem I gave you. So that is, you have to transport this triangle here and all that. If you are, it is mostly people will be happy with that. So that is the proof itself. But a very definite thing always axiom, that is not there. But definite method is there always, you see. And always there is a way of finding the correct this thing and wrong application. It's called upapattis. Yeah. I will just introduce this and then stop. So the trigonometry the Indian way. Okay. So trigonometry formulated in the Indian way played a crucial role in algorithmic formula abundant nature of mathematical astronomy in India. Okay. So what they do is this, suppose there is a circle of radius r. Okay. So have this, OA is the radius, you drop, and this is the diameter, you drop a perpendicular. So this is r sin theta, this is called ja. So whenever normally ja, you have to give the radius, so it is a length, the sine function is the length, not a ratio. So r sin theta, so normally it is taken to be 21,600 by 2 pi, nearly 3438 for an angle theta or r cos theta. Okay. And the ja is r sin theta, and this OB, that is the r cos theta or koti ja, and modern sine is essentially the Indian ja except for the factor r. Whereas the Greeks also had, they also had trigonometry. So that is the relation between the arc and the chord there, you see. So here AC is the arc and this AC, this is the chord. So AC is, they are related actually. AC is chord of 2 theta, it is 2AB into 2R sin theta. Okay. So Indians, it's possible that they borrowed from the Greeks regarding this chord. Okay. But then they said jardha, they say, jardha, ardha, half of that is more convenient. Okay. So earlier they used to call it jardha, and finally, eventually that ardha got japped, and ja is the related, what is called ja only was used. Okay. In all calculations, it is a sign that appears, and Indian sign is perfectly suited for writing formulae and calculations. Chord is far less so. So that is the importance of this Indian version of trigonometry. As a matter of fact, the word sign also is related to ja, though it doesn't appear so. You see, ja also called jiva. Ja and jiva both are used in Indian, mostly in astronomy they were using, and it is adapted by Arabs, and jiva becomes jeb, jiba, then became jeb. Jeb becomes pocket or bosom, things like that, chest cavity like that. Okay. So jeb or pocket or fold, and it was translated into Latin as sinus. So sign, ja to sign. So this is acknowledged by most scholars. So the term sign is derived from Indian jiva. Now the complement of ja is koti ja. So complement of sign is cosine. So ko is very much there, koti, you see, koti ja, sine and cosine. So this is the origin of this, sine, cosine. So because koti is what comes in India. Okay, yeah. This will be the last slide. See how this applied. I don't want to get too technical. see what is the duration of a day, that means sunrise to sunset. Okay. So, sunrise to next sunrise is 24 hours. So, sunrise to sunset, how much is it? So, typically average is of course 12 hours, but it is not so throughout the year. Okay. In Chennai it is somewhat close, in equator it will be always 12 hours. Well, Chennai will be slight variation will be there. And if you go north, you would have seen, many of you would have gone to or into Europe and all that, you see. I mean, till 9 o'clock in the night, the sunlight is there, and 4 o'clock itself will start and things like that, you see. So, why is that? So, that is the problem which is even addressed by Aryabhatta, but it does not give all the details. Later they give the details, you see. And the duration of, see, suppose this is the path of a object in the sky. So, this is called a 6 o'clock circle. So, normally in Lanka it is always this, whereas in any place, suppose you have some between March 21st and September 23rd, this will be in this kind of a circle towards north of equator. So, then when this is the extra time bit, and similarly here also. So, this is called chara in India, and this expression chara is this. So, this is expression for chara given in Indian text from Aryabhatiya onwards. So, this is the chara. Of course, they do not write it like this, they will say that take the or sin phi is called akshajya, then or sin delta is called krantijya. So, take akshajya, multiply by krantijya, divide by jujya, that is or cos delta, and also divide by lambajya. Okay, you now get that number. Okay, and then take the arc of that and express in Gatikas. So, add and subtract like that, you see. So, that is the thing. So, this formula is there. So, no such expression in Ptolemy's Almagest. There is no such, because Ptolemy was considered the greatest figure in astronomy, you see, from let us say some 2nd century AD to 15th century. There is only Ptolemy. Everybody followed Ptolemy. There are no important things. Of course, some Arabs and all that made some innovations, but the basic thing is that. So, he gives whole lot, of course, it is a great work, nobody can deny it. It is a very great work. Geometrical models are there for everything. He explains how things are done, all true, but there are no formulae. Whereas in India, in sutras, they give the formula, which can be done, you see. And this is not emphasized by these historians of mathematics, okay. Formulae are given, they may be given in terms of shloka, okay, but it is has a definite meaning. You can write, now we can write down, okay. Then also they could, I suppose, write down on these things, on some kind of a phalaka, or some wooden board or some sand and all that, you see. So, the formulae are there, and whereas it is missing, and we are used to formulae, right, everything is written a formulae, and that is because of the Indian way of thinking, you see. Algorithm is there, and then so it is natural to talk of formulas and all, and this is there, you see. And what makes this Indian trigonometry way it is done, so it is easy to write the formulae, not only for this, there for planetary positions and all that, you have a formulae. So, this is, I will stop here. Next time I will go a little bit more into trigonometry. Happy or little apprehensive? I am sorry. The thing is, probably I don't know, too many concepts might have been used, so it may be difficult to hold, but they are not all, I mean, you can see that they are all some things which you are used to, but not in this way, okay. See, after all, algebra, permutation combination, okay, apple orange formula, you see, and you have to know it very well to clear JEE. Okay, so all permutations, combinations, geometry, the so-called Pythagoras theorem, you see. So, I am relating the Indian things which are there, in that, okay. And the series, okay, maybe infinite series, I don't know whether you came across, I have come across in school, you have come across infinite series, yes, yeah. The first infinite series was here in India, around 1370 like that, by Madhava, okay. So, first way in time in which a infinite series was written. So, it is all these things, but maybe too many things have been said, but you can take a copy of this and you can think about it at leisure. Which one? Which formula?
So, what is the proof for the formula that's given in this slide? How did we get the duration of daytime?
Of the?
Daytime as 2 into.
That one, yeah, that one. Yeah, that is this, you have to follow the geometry, See, this is the, see this from here, to here. You see, then that is, that corresponds to, 180 degrees, okay. This is 90 plus this is 90. And what is the corresponding to this, how much is that, okay. They give the derivation. Brahmagupta gives the derivation for that. Not Brahmagupta is a commentary, he gives the derivation. Bhaskara one also gives the derivation, okay. So, then depends upon this so called declination. This extra angle you have to find out. So, that depends upon the declination. It depends upon the latitude. You see, the celestial pole, altitude of celestial pole is equal to latitude of a place, okay. So, then one can find out this, and that is what you give, so it is derived, okay. It takes a little bit of time, yeah. Which one? You want me to go? Yeah, yeah. You have some question or you are admiring it? If you are admiring, that's good, Yeah. Tell me, yeah.
For
Yeah.
the combination question,
Yeah.
how do we know that they actually had a general formula for it and they didn't just solve for that one particular case?
General formula for?
Permutations and combinations.
This is Bhaskara gives the result. Bhaskara gives, if you take n digits, okay. So, then what is the number of ways it can be arranged? See, using the same digits, okay. So, then it is factorial n, okay. And if some of them are digits are alike, p of them, and q of them and all that, he gives the formula. He states it in a verse. Yeah. Of course, he doesn't say use the symbol factorial n. See, what he says is, you take n, then keep on subtracting 1 from that, okay, and go up to 1 and multiply all this, okay. So, n into n minus 1 into this thing, okay. He doesn't use the symbol factorial n, but this is what he means, yeah. No, that's not true, that's not true. See, first number 1, the symbols, I didn't talk about symbols, but symbols are very much there. Even Bhaskara one, this is called Yavat Tavat, okay. Yavat Tavat was this thing they will use, So, they use that symbols and express the equations, especially Bhaskara. In fact, I am working on Bhaskara's what is known as Siddhanta Shiromani. So, they write the equation, you see. Okay, so let's say x squared, okay, is equal to b. So, what he says is for x, this thing they say yavat. Now, typically the symbol ya is used for unknown quantity, avyakta, yeah. So, they write it like this, ya va. See, va means varga, the square, okay. So, then they just write a is some other quantity, okay. So, they will call it, let us say a, okay, and then they will say ya, okay, and they will say 2 and they will put a dot, okay. So, this is, it understood that this and this have to be added, but minus sign is there, so dot was used, okay. So, now for the b, so let us say ba, okay. So, ba is written below. So, that is how it used to be written. So, many more of these things are also there, you see.
So it could have been formulated in this way before the advertised problem.
Yeah. See, for instance, of course, this is he gives some algebraic solution and all that. Now, quite sophisticated results in spherical trigonometry are given, solutions are given, you see. So that they would have certainly had methods to do it, So everything may not be proved in the work, but with Bhaskara, in his own commentary, he gives the detailed way how it is, proved. Okay. See, for instance, you have, some formula. I don't want to bore you too much, but this is known as the formula for zenith distance relating it to hour angle and declination and latitude and all that. Yeah. So he says those things, those things are said, okay, and very clearly this thing, expressed. So these things are no. So derivations are also given. Full derivation is given, especially in Bhaskara's thing. Full derivations are given. Yeah. Number two, see, spreading. See, that is some kind of a common notion that we didn't have any method of, transmission. Transmission was not there because it was confined to some people, and then because of the way it was expressed, you see, it is not, that is not quite true. You see, common people didn't have, that is not true. See, for instance, what is the first scientific work in an European spoken language? See, that is, I think only Galileo did it in 17th century beginning. Okay, the dialogue of two words and other, that was written in Italian. Earlier, everything was in Latin. Okay, and Newton also wrote in Principia. So that was in Latin only. Whereas in India, you have got 16th century beginning itself, Yukti Bhasha is written in Malayalam. You see, so it is there. There are many other works also in other regional languages, like Kannada, Marathi, and other. They are there. Telugu, they are there. So and number two, so there was a variety of books, like Siddhantas, and then Karnataka, simpler things with simpler manipulations and all that. You see, so that rich variety is not to be seen in these things, India. So somehow there is this misconception that they didn't have a way of transmitting it, because there are plenty of, there are supposed to be 1 lakh manuscripts on Jyotisha in India, out of course many of them will be astrology. So it is estimated 20,000 manuscripts are there, but they are all not new thing, or they are copies of, many of these things are copies. But so there was transmission, kind of a thing. So that is there. In some circles, for theoretical details in smaller circles, but practical thing, I think more people could know in the way of that kind of books also were there, which had less theory and more calculation with simple arithmetic. Yeah, they are there. Yeah, I am not saying that but now you have more formulation, more better ways of expressing things, and everything is not. I am not saying that but there are equations. You see, if Bhaskara gives the details of using algebraic methods to solve some astronomy problems, they are there, and he writes in terms of equations and how to solve this equation and so on.